The Ideal Adsorbed Solution Theory is extensively used in the description of mixture adsorption equilibrium in microporous materials such as zeolites and metal organic frameworks. It is important to realize that the applicability of the IAST relies on a set of key tenets. The first one is that the adsorption sites should all be equally accessible to each of the guest molecules in the mixture. This implies a homogeneous distribution of guest adsorbates within the pore landscape of the microporous material. There should be no segregation or congregation or preferential siting of any of the guest molecules within the pore structure. And molecular clustering should not occur, implying that there is no change in specific surface area of each molecule on mixture adsorption, and that the surface area occupied by each guest remains the same, whether it's a pure component or a component in the mixture. Now, there are many instances in which one or more of these tenets are violated, and I describe each of these violations in several publications of mine. I list here the three most important ones. I've also prepared YouTube presentations on the departures from the IAST and the failure of the IAST. These can be viewed on my YouTube channel. My objective today is to discuss the modeling of non-idealities within the adsorb phase when one or more of these tenets is violated. Take the example of mixtures of carbon dioxide and propane adsorption in LTA4A zeolite. LTA4A zeolite consists of cages of approximately 11 angstrom in diameter. Each cage is separated from adjacent cages by narrow 4 angstrom windows. The extra framework cations or sodium cations indicated here as blue spheres. For this example of mixture adsorption, the carbon dioxide preferentially locates at the window regions as shown in this computational snapshot. And the propane molecules, on the other hand, are located within the interiors of the cages. Therefore, a CO2 molecule that is firmly ensconced at the window side does not have to face stiff competition with the propane molecules that are located within the cage interiors. For small compositions of CO2 in the bulk gas phase mixture, the mixture adsorption equilibrium is in favor of CO2. Only with increasing mixture composition that the adsorption selectivity reverses to favor the propane molecule. Indeed, for bulk CO2 compositions of 0.1 mole fraction, we have azeotropic adsorption, shown by these points here. So this is an example of thermodynamic non-idealities engendered due to non-homogeneous distribution of gas molecules within the pore framework. Let's see how we model deviations from the IAST by introduction of activity coefficients, so that we may be able to quantify the phenomena of azeotropic adsorption. In the Myers-Prausnitz theory of mixture adsorption equilibrium, the partial fugacities of each of the gas components in the bulk fluid mixture is related to the mole fractions x sub I in the adsorbed phase by this expression, which is a generalization of the expression for description of mixture adsorption equilibrium in fluid mixtures. P sub I superscript 0 are the sorption pressures of the species I, and gamma I is the activity coefficient of species I in the adsorbed mixture. The sorption pressures are such that the spreading pressure for mixture adsorption equilibrium is the same as the spreading pressure for component 1, and the spreading pressure for component 2, the spreading pressure for component 3, and so forth. The spreading pressure is denoted here by the Greek letter P or pi, and it is convenient to define a surface potential, which is a product of the spreading pressure in the units of newtons per meter multiplied by the surface area per kilogram divided by the gas constant R times the absolute temperature in Kelvin. The spreading pressure has the units of moles per kilogram. These can be determined from the fits of the unary isotherms for each of the components in the mixture. The surface potential phi is a proxy for the spreading pressure. And if we define the pore occupancy as theta, then the pore occupancy is related to the surface potential by this expression, where Q sub sat mixture is the saturation capacity of the mixture. So the surface potential also serves as a proxy for the pore occupancy. Now, all of this formalism is described in my paper, How Reliable is the Ideal Adsorbed Solution Theory for Estimation of Mixture Separation Selectivities. I invite you to look at my ACS Omega paper and also see the relevant YouTube presentations. My task today is to see how to set up models to describe the activity coefficients in the adsorbed phase. The setting up of models for description of activity coefficients in bulk fluid mixtures is well known. The excess free energy divided by RT is x1 ln gamma 1 plus x2 ln gamma 2, and it is common practice to set up models for the activity coefficients such as the Margules model or the Wilson model in this form that have the proper limiting behavior that the activity coefficient of any species I tends to unity when the mole fraction of that component tends to unity. Indeed, in the literature on mixture adsorption equilibrium, the very same relations for the Margules equation, the Wilson equation, or the inertial equation are used to describe activity coefficients in the adsorbed phase without further modification. And let us examine the limitations of this approach, where the activity coefficient models are the same as used for bulk fluid mixtures. Before setting up the proper activity coefficient models to describe mixture adsorption equilibrium and departures from the IAST, we need to have an understanding of the characteristics of the activity coefficients. In order to do that, we carried out configurational-bias Monte Carlo simulations of mixture adsorption of CO2 and propane in LTA4A zeolite. The CBMC simulation are described in my papers listed here. We carried out two types of simulations. Firstly, simulations at a total bulk fugacity of 1 megapascal, and the composition of the bulk gas phase mixture is varied from 0 to unity, and the component loadings determined from CBMC simulations. From the CBMC simulated data, we can back calculate the activity coefficients in the adsorbed phase, and these are plotted here, which shows the red circles are for CO2 and the green squares are for propane. These activity coefficients are plotted as mole fraction of CO2 in the adsorbed phase mixture. We see that as the mole fraction of the adsorbed CO2 approaches unity, the activity coefficient also approaches unity. The same is true for propane. As the mole fraction of propane increases to unity, in other words, the CO2 in the bulk phase is practically 0, then the activity coefficient of propane is unity. So we have gamma I tends to unity when xi tends to unity. This is the same as for bulk liquid mixtures. However, there is an additional limiting behavior that needs to be respected and followed, and that is shown in this these two figures, where we show configurational-bias Monte Carlo simulations for mixtures of CO2 and propane in which the bulk composition is fixed at the value of 10% CO2 and the total bulk fluid phase fugacity is varied from 1 Pascal to 1 megapascals. With increasing bulk phase fugacity, the pore occupancy increases progressively, and we see here that the IAST predictions become increasingly poor, especially for CO2. If we back out the activity coefficients in the adsorb phase mixture and plot it as a function of the surface potential, we see that as the surface potential is reduced to vanishingly small values, this also implies that the pore occupancy is vanishingly small. Then the activity coefficients of both components approach unity. So the activity coefficient models that describe mixture adsorption equilibrium must also respect the limiting case that gamma I tends to unity when the surface potential tends to 0, that is equivalent to saying that the pore occupancy tends to 0. So we have an additional requirement for the behavior of the activity coefficients when we set up models to describe activity coefficients in adsorbed phase mixtures. This point is not often stressed enough in the published literature, as I stress in my published papers. In setting up the activity coefficient models for describing non-idealities in adsorbed phases, we need to have the models respect both these limiting behaviors, that gamma I for each of the components tends to unity when the adsorbed phase mole fractions of that component tends to unity. In addition, we must ensure that the models respect the limiting behavior that the gamma I for each of the component guests tends to unity at vanishingly small pore occupancies, that is equivalent to saying that the surface potentials are vanishingly small. So say we use the Margules model, we need to introduce a factor, a correction factor that describes the pore occupancy. The correction factor is 1 minus exponential of minus phi divided by the saturation capacity. We may replace this expression with another expression where we introduce a factor C, and C is to be interpreted as the inverse of the saturation load capacity of the mixture. And we may model activity coefficients in the adsorb phase by using, say, 3 parameters, A12, A21, and C. This approach is described in detail in my 2 papers listed here, both of which are published in ACS Omega. I stress once again that this correction factor is often ignored, and this does not afford the proper limiting characteristics that the activity coefficient models must obey at vanishingly small pore occupancies.